joint work with Greg Bodwin, Keerti Choudhary, and Merav. And today we will talk about new fault-tolerant subset distance preservers. This work is about fault-tolerant distance preservers. Now let me start with a general definition of a distance preserver. The input for this problem is a graph G and a set of node pairs P, where the goal is to calculate a sparse subgraph that preserves exact distances between the pair nodes of P. So here in the illustration you can see that the distance between the yellow pair node is exactly the same in H and in G, and same goes for the green pair. But in H, we try to make it as sparse as possible. So formally, for every pair nodes in P, we require that the distance between them in H is the same as the distance between them in G. So clearly we can take H equal to G, just take all the edges in the graph. It is always the distance preserver, but our goal is to make it as sparse as possible. So our work focuses on the special case where P equals to S times S. So now we say that all nodes are yellow, they're all part of the same set, and we had to add some edges to H to make it a preserver of S, meaning that for every pair of nodes from S, the distance between them remains the same in H and in G. So this is called a subset distance preserver, and it is quite common. It is actually one of the primary reasons distance preservers were first developed. One of its main applications is in communication network in real-life graphs, where parts of the graph can spontaneously fail. So what happens if there is a failure in this network? As H is very sparse, the failure can completely disconnect it, while G, not even that G is still connected, the distance between the yellow nodes is not even harmed. So this motivates an additional requirement, which is called fault tolerance. So a subset fault tolerant preserver, we are given a graph G and a set of nodes S, and our goal is to have a sparse subgraph that preserves exact distances between the pair nodes of S upon a failure. So what do I mean? If there is a failure, then H minus X is still a preserver of G, meaning that in the presence of a failure, the shortest path between every yellow node is the same. And this holds for every possible failure. It may be also this one. And formally, we say that for every pair of nodes from S, the distance between them in G minus X is the same as in H minus X, and this holds for every two nodes from S and for every fault X. And I will also mention that the definition for fault tolerance for edges is the same, except X is an edge. But this work is about vertex fault tolerance, so when I say fault, I usually mean a vertex fault. So now we added enough edges to H to say that H is resilient to a singular vertex fault. Our work is about fault-tolerant subset distance preserver. There are various settings in which one can learn fault-tolerant preservers, which include directed and undirected graphs and weighted and unweighted graphs. So let's begin with undirected graph. So the state of the art so far, first we begin with the single pair edge fault-tolerant case. So this is the case where we have S and T, and we have the path between them, and any edge on this path can fail. And what we want in our fault-tolerant preserver is that for any such edge, we want the shortest path between S and T without this edge. So Bodwin et al. Showed a linear bound on this problem. Okay, so next, a result by Bilo et al. Is O tilde of NS for subset edge fault-tolerant preserver. And this means that we have a set S, just like we showed before, and we want to preserve the distances between this set following a failure of an edge. So current literature reflects a world in which vertex faults are harder to analyze than edge faults. And many other questions in this area are closed for edge fault tolerance, but open for a vertex fault. Another interesting result is the one of Coppersmith and Elkin, and an upper bound of O of NS for subset distance preserver in the fault-free setting. And note that this is very close to the state-of-the-art result for edge fault tolerance, and we'll talk about it in the next slide. So our result in undirected graph, so given an n-node undirected weighted graph G and a set of nodes S and the subset, we say that the subset vertex fault tolerant preserver has at most O tilde of ns edges. And when S is equal to 2, meaning that we only have one single pair, this bound improves to be strictly linear. We also add a matching lower bound, which means that for every size S of source nodes and for every n, there is a weighted graph with at least ns edges for its subset vertex fault tolerant preservers. So not only that our result is as sparse as the subset fault tolerant preservers for edge fault, it is also almost as sparse as the known upper bound for the fault in the fault-free settings proved by Coppersmith and Elkin. And I believe that this reflects the weakness of our current understanding of non-faulty subset distance preservers, rather than the thought that fault tolerance is actually for free or for log n factor. Still, non-faulty subset distance preservers bound have resisted improvement for the last 15 years, so this unintuitive hypothesis of free fault tolerance may be hard to refute. Our hypothesis is that in the bound of current knowledge, the presented lower bound holds in the unweighted case as well. So this completes the picture with regards to undirected graph. And let us consider directed graphs now. So in directed graph, the only non-trivial result is the one of Bodwin et al. Showing that for a single pair fault-tolerant preserver, which means that we only consider one S and one T, and we want to preserve the distance between them no matter what edge fails. So such a preserver, they show that the correct size bound is exactly that of a non-faulty distance preserver in the fault-free setting of n demand pairs, which bounds were given by Coppersmith and Elkin. As you can see, it is at least n to the 3 over 4 and at most n to the 3 over 2. The most interesting case that was left open by the Bodwin et al. Work is the one of directed and unweighted graphs. For this case, we provide the following result. So for directed unweighted graph G, a set of sources S and a fixed root R, we define P to be R over S, meaning that we always have R and some vertex for S. This is our pair set. So there is a fault-tolerant preserver with O tilde of n to the 4 over 3 and S to the 5 over 6 edges. And when S is equal to 1, which means that we only have one single pair to consider, this bound improves to be O of n to the 4 over 3. So like before, we also show conditional tightness of this bound, meaning that until there is improvement in the fault-free setting, we believe that this is optimal. Okay, so lastly, we turn to weighted directed graphs, and we show that for directed weighted graph G and with the same setting and definition of P, there is a fault-tolerant preserver with O tilde of n to the 3 over 2, S to the 3 over 4 edges, and this extends the state-of-the-art by Bodwin et al. So in today's talk, we focus on our first result in undirected graph. So just to remind you of the problem, we are given an undirected graph G and a set of sources S. And let's go carefully through the output. So our H is defined to be all the edges in the replacement path PSTX, when S and T are the sources and X is the failure, and when a replacement path PSTX is defined to be the shortest path from S to T in G minus X. So you have a yellow illustration of this replacement path, and also let's remember that it's parameterized by 3 vertices, which is the source, the target, and the failure vertex X. Okay. So a bit of notation, we use TS to denote the shortest path tree of S. You can think of the BFS tree in an unweighted graph. And T of big S is just the union of all these paths. So our algorithm is as follows. First, we add all of this shortest path tree to H, and this cost us O of S n edges for each tree. And next, we carefully choose n log n additional edges for every source node, ending with ns log n for the entire preserver. So our technique is based on two simplifications, which we can do without loss of generality. The first one is that we allow ourselves to analyze short replacement path only, and this is due to a heading set argument. And the second one is we use a reduction from general vertex fault in the tree of Ts to a specific case where the fault occurs on a path in Ts, and this reduction is based on the useful tool of heavy path decomposition. We will talk about it shortly. So first one is we observe that it is enough to consider only short replacement path. So we define PSTX to be short if the number of edges in PSTX is no more than n over s edges. And we define P short to be all the short replacement path that we want to preserve. So our claim is that it is enough to bound all the edges in P short only, and this is by a heading set argument. We can sample O of S random vertices, and then in every long replacement path, we have that each edge on a long replacement path is actually in between some two new sources, and the path between them is at most n over s. So it's actually each edge on a long replacement path is actually on a short replacement path, and this is why it is enough to consider only edges in short replacement path. So the second simplifications, which allow us to consider faults only on a path, for that we use the heavy path decomposition. And this is a decomposition of a tree Ts into vertex disjoint paths that was introduced by Celador and Tarjan. So the input for this decomposition is a tree Ts, and the output is a partition of the tree to vertex disjoint path, which have some useful properties. So just to be on the same page, let me briefly explain how this decomposition can be computed. So a basic definition is that of a heavy child, which is the child with a maximal subtree size. And the decomposition is made by just following each time from the source to the heavy child, like this. So the desired decomposition is obtained by recursively applying this process over the remaining subtrees. So now we're done. Okay, so a useful lemma is that for any vertex V, its path to S in Ts intersects at most log n paths of the decomposition. So let us consider V and the yellow path. We'll just give the intuition for that. So any black edge means that we did not have an heavy child, and this means that the size of the subtree is cut by at least by half. So this is why we can have at most log n such edges. And this will be very useful in our analysis. So we now turn our focus to edges of replacement path with failure on a specific Q, when Q is denoted by x0 to xk. We define H as Q to include all the replacement path with x, the failure, on Q, and T from S, which are all out of our interest replacement path anyway. So our goal is to bound the number of edges in HSQ to be the same as NQ, where NQ is the size of the subtree rooted at x0. So again, since we want to use the heavy path decomposition, we want to analyze Q locally, which means that we want to be depending not on the entire number of vertices in the system, which is n, but in a smaller n, which is only the number of vertices in the subtree rooted by x0, which is a subtree including Q. So our strategy is as follows. For every replacement path, how do we handle it? We partition to several classes the So we have many kind of replacement paths, each with a failing vertex on Q. And what we are doing is to partition them into classes depending on the location of the target T with respect to the failing vertex. Then the edges in each class will be bounded separately. So let us fix Q and S, and actually we also fix the classification is with respect to the failure. So let us fix a failure, and we divide T minus the failure into 3 parts, and this partition was introduced by Botswana and Kahana. So first part is UI, which includes all the shortest path tree minus the shortest path tree rooted at xi, like we see in the painting. Second part is DI, which is the subtree of the vertex in Q that follows our fault, like we can see in the illustration. And the remaining part is just the part in between, just like we see in the illustration. So we have 3 options for tree where T can be the target. I remind you that S is fixed now, X is fixed now. So only thing that define the replacement path now is T. So T can be in UI, T can be in OI, and T can be in DI, and those actually our classes. So when T is in UI, then actually this path is already in the shortest path tree of S because it is not on the subtree of the failure, meaning that the failure was never on the original path from S to T. So this was easy. And for the case that T is in OI, we use a counting argument which relies heavily on this fact that Xi is the LCA of T and Xk. So let me just convince you by that. So if T was here, for example, so we expect the LCA to be somewhere here, and if T was here, we expect the LCA to be somewhere here. So indeed, we have that T is in OI if and only if Xi is the LCA of T and Xk. So actually, the counting argument is based using the happy path decomposition. We know that we have at most log n q's such that xi is really on the path to q, and we have I remind you that we have only short paths. So this means that we have enough edges to add all the replacement paths with this property. So the counting argument said that it's not too many edges to just add all the short replacement paths with this property that T is in OI. Okay, so next we have the most involved case where T is in DI, where this is DI, and the yellow nodes are the options for T. So fix xi, and we have T and DI, and the replacement path looks somewhat like that, and I will not go over it. I will go over it shortly just to give you the intuition. So in this class, we ask which edges of the replacement path are already in H. And for that, we define some special vertices. For example, this vertex, which we know that by our previous argument, we know that this path is actually already in TS. And we also define this vertex, and we show that this path that you see right now is actually in TT, since the failure xi cannot be on its shortest path to T. And this is how all that's left for us is that this small segment in the painting, which might be long in reality, to handle. So what are we going to do? Our strategy for any xi, for any failure, we embed this shortest path into a smaller graph g hat I with O of OI nodes. So there may be several replacement paths with path in here, and we define a new graph which contains also edges which are not in G. Then we compute a shortest path tree in G hat I, and we use it in order to decide which edges from G we can add to H. And this shortest path in G hat I covers all of this replacement path. In addition, we add the following edges in the endpoint for every replacement path, and this gives us a bound Okay, so we also use the fact that OIs are mutually disjoint, so you can see it in the picture quite easily. So the summation over all OIs, over all failures that possibly can happen on Q, is O of NQ, which is the size of the subtree rooted at the beginning of Q. So this is what we wanted. So to sum up, if HSQ is all the edges in the replacement path where the failure is an Q, so the size of it, we can show that it's O of NQ, and the number of such replacement paths. As you recall, we added 2 edges for each replacement path. So actually, this is a good point to mention that for S, which is only a single pair, which for the case of single pair, we get a linear bound here since NQ is equal just to N. If we take Q to be the shortest path between S and T and apply this analysis, then the Q is the path between S and T, so NQ is just N, and the number of replacement paths, so T is fixed, and X in Q, it is bounded by N, since this is the bound over a length of shortest path, so we get a linear bound here for a single dement pair. So, but in the general case, we have many Qs from the heavy path decomposition, and we would like to check how many edges do we add overall. So let's check this out. So first we bound the sigma of NQ. So a reminder is that each vertex appears at most in log n subtrees of Q. So we can participate in at most log n subtrees rooted by the first vertex of Q. So V is actually counted here in the left hand side at most log n times. So this is why the summation is O of n log n. And to bound the number of replacement paths, so actually PSTX with X and Q, since the Qs are a partition of TS, then this is a partition of the replacement paths that we have, and they are mutually disjoint. So how do all we need to bound is really the number of short replacement paths from S, which is PS. So how do we do it? We defined PST, which is includes all the replacement paths from S to T. And then we show that it is actually sufficient to show that for every T, the replacement paths from S to T are no more than N over S. So again, why is this enough? Since we have S such T's, then it shows an immediate bound on PS that we have O of N such paths. So now all that's left for us is this way, and I don't know if I will have time to show you the weighted case, but let us begin by the unweighted case. So if the replacement path is short, it means that the path between S and T is short, and it has at most N over S edges. And like we said, a replacement path PSTX, so S is fixed and T is fixed, and for X we have only N over S possibilities, so this gives us a bound on the number of replacement paths from S to T. And for the weighted case, so I will just give a proof sketch for any replacement path with failure in here, where in here I mean between S prime and T prime, which are in distance from S and from T. And we know that it must avoid all of these segments, otherwise it wouldn't be short. So again, we have a fixed S, a fixed T, and for X, we have only N over S possibilities between S and S prime, and N over S between T prime and T, and one more for the one in the middle, and we finish with at most N over S possibilities for failure as well. So putting it all together, we show that the union over all paths in the heavy path decomposition is no more than n log n edges, and summing this over all S yields the desired bound of O tilde of ns. So this summarizes the main idea of our approach, and I'll be happy to answer any questions in the QA session. And thank you for your attention, and I hope you enjoy this talk.